As you settle in tonight, wherever you are right now, maybe the room is dark, maybe there's a lamp still on somewhere nearby, casting that soft, quiet glow across the ceiling. Light is arriving at your eyes. It has been doing this all day. It will do it again tomorrow. And you've never once had to think about it. Light just comes. It just is. It feels as natural and unconditional as breathing. But here's the thing. That light reaching your eyes right now, even from a lamp just a few feet away, has traveled at a speed so extreme, so cosmically strange, that it quietly breaks several of the most deeply held assumptions about how reality works. And the light coming through your window from the stars, some of it left its source before your great-great-great-grandparents were born. Some of it has been traveling since before the dinosaurs walked the earth. And it arrives here, right now, at your eyes, in this quiet room, without slowing down even slightly. Not by a single fraction of a meter per second. We're going to take that fact seriously tonight. We're going to sit with it. Turn it over slowly. Look at where it comes from and what it means and what it did to the people who discovered it. If you drift off somewhere along the way, that's perfectly fine. The ideas will still be here. And honestly, some of the most beautiful things about this story are the kind of things that settle better when you're not trying too hard to hold them. So let's begin where most of the best science stories begin, not with a grand discovery, but with a simple question no one had thought to ask carefully enough. For most of human history, people assumed that light was instantaneous, that it didn't travel at all, really, at least not in any way that mattered. You lit a torch, and the world around you was immediately illuminated. You struck a flint, and there was fire and light at once. The two seemed inseparable, simultaneous. You couldn't imagine one without the other arriving at the same moment. Even the ancient philosophers who thought most carefully about the nature of the world couldn't quite agree on this. Aristotle believed light was not a thing that moved through space at all, but rather a state, a kind of activation of the medium between the eye and the object. Sort of like how pressure travels through water when you push it. You push here, the effect appears there, but nothing actually travels between the 2 points. At least, not in a way you'd easily notice. Euclid and the other geometers of antiquity were more interested in the direction of light, the way it travels in straight lines, the way it reflects off polished surfaces, than in the question of its speed. And you can forgive them for this. In the everyday world, the question of whether light has a finite speed is genuinely unanswerable by casual observation. You can't notice a delay between a lightning strike and its light reaching you from across a field. The delay would be measured in billionths of a second. You do notice the delay between the lightning and the thunder, and so people concluded that sound travels through air, slowly, but light must arrive all at once. Roger Bacon, the 13th century English friar and early empiricist, wrote that light propagates with finite velocity, not instantaneously. But he couldn't prove it, and the idea didn't gain traction. It was just an intuition, a philosophical suspicion. Then came Galileo. And this is one of those moments in the history of science where you love someone not for their success, but for the sheer audacity of the attempt. Galileo Galilei was, among many other things, a man who refused to accept that something couldn't be measured just because nobody had measured it yet. He is most famous for his work with the telescope, for his confirmation of the Copernican system, for his run-in with the Inquisition. But tucked inside his long career is this quiet, almost charming failed experiment that belongs in the story of light. Sometime in the early 1600s, Galileo tried to measure the speed of light. His method was direct, almost naively direct. He had two people, let's say himself and an assistant, stand on hills about a mile apart in the dark, each holding a covered lantern. Galileo would uncover his lantern. The moment his assistant saw the flash, he would uncover his own. Galileo would measure the time between uncovering his lantern and seeing the return flash from his assistant. He did this. He tried it. And the result was nothing. The return flash seemed to come back instantly. The delay, if any existed, was too small to measure. He repeated it at longer distances. Same result. What Galileo concluded, to his credit, was not that light was instantaneous. That would have been the lazy answer. He concluded that if light had a finite speed, it was simply too fast for this method to detect. The round-trip time for light to travel a mile was far too small for human reaction time to catch. That's a beautiful conclusion. He didn't prove what light's speed was. But he proved his own method wasn't good enough. He identified the right question and acknowledged he couldn't yet answer it. The answer would have to wait for a man named Ole Romer, who wasn't looking for it at all. Ole Romer was a Danish astronomer, born in 1644 in the small town of Aarhus, and he spent a significant portion of his career doing something that sounds, on the surface, like some of the most tedious work imaginable. He was meticulously tracking the eclipses of Jupiter's moon Io. Now, Jupiter has 4 large moons, first properly observed by Galileo in 1610. These moons orbit Jupiter with beautiful clockwork regularity. Io, the closest of the 4, whips around Jupiter in about 42 hours. And because its orbit is nearly edge-on from Earth's perspective, it regularly passes behind Jupiter and disappears from view, an eclipse, before reappearing on the other side. These eclipses were predictable, periodic, reliable. In the 1660s, the Italian astronomer Giovanni Cassini, and yes, the same name as the Saturn probe, because scientists keep naming things after their heroes, had actually noticed something odd about Io's eclipses. At certain times of year, they seemed to arrive earlier than predicted. At other times, later. The discrepancy wasn't huge, but it was real, and it was systematic. It seemed to follow some annual pattern. Cassini suspected this might have something to do with the speed of light, and he said so, briefly, but then he moved on without pursuing the idea. Something about the implication made him uneasy, or perhaps he simply didn't follow the thread far enough. Romer followed the thread. He began his own careful observations of Io in 1671, working first with Cassini in Paris and then continuing on his own. And over 4 years of patient, almost obsessive observation, night after night, winter after winter, filling notebooks with eclipse times, he assembled a pattern that was undeniable. When Earth was on the same side of the Sun as Jupiter, close to it in its orbit, the eclipses of Io arrived on time. But as Earth moved around in its orbit and ended up on the far side of the Sun, as far from Jupiter as it could get, the eclipses arrived about 22 minutes late. And then, as Earth swung back around toward Jupiter again, they gradually came back to the predicted time. Romer understood what this meant. Light wasn't instantaneous. It was taking extra time to travel across the additional distance, the diameter of Earth's orbit, when Earth was on the far side. He was watching the finite speed of light in action, written into the clockwork of Jupiter's moons. In 1676, he presented his findings to the French Academy of Sciences. He estimated that light took about 22 minutes to cross the full diameter of Earth's orbit. Using the best estimates of that orbit size available at the time, this implied a speed of light of roughly 220,000 kilometers per second. This was wrong, as it turned out. The actual speed is about 299,792 kilometers per second, and the travel time across Earth's orbit is about 16.5 minutes, not 22. But Romer's method was completely sound. His error came from inaccurate knowledge of how wide Earth's orbit actually is, something that hadn't been precisely measured yet. The logic was perfect. The technique was right. And the conclusion, that light travels at a finite, measurable speed, was correct. The reaction from the scientific community was mixed. Some embraced it enthusiastically, among them the Dutch physicist Christian Huygens, who used Romer's data to estimate the speed of light with reasonable accuracy. But others were skeptical. The idea of light having a travel time was still counterintuitive, still hard to accept at a gut level. Even Cassini, who had noticed the anomaly first, backed away from the light travel interpretation and suggested other explanations. Romer returned to Denmark, became the Astronomer Royal, introduced standard units of measurement, redesigned the streetlights of Copenhagen, created the first reliable thermometer in the region, and died in 1710, having contributed more to human knowledge than most people even notice. And the speed of light, once he had established it as finite, became one of the great obsessions of the next 2 centuries. What was the exact value? And what was light exactly? These questions would turn out to be deeply connected in ways no one yet suspected. Before we get to the measurement, let's talk for a moment about the nature question, because it runs parallel to the speed question and eventually collides with it in the most spectacular way. What is light? For most of history, there were 2 competing camps. Some people, Isaac Newton among them, believed light was made of particles, tiny corpuscles flying through space. Newton had excellent reasons for this view. Light travels in straight lines. It bounces off mirrors the way a ball bounces off a wall. It doesn't bend around corners the way sound does. Particles made sense. But there was evidence on the other side too. Light does strange things when it passes through a narrow opening or near the edge of an obstacle. It spreads slightly. It creates fringes of brightness and dark. These fringes looked, to some observers, like what you'd expect from waves interfering with each other, the way ripples in water spread and overlap and cancel each other out in certain places. Christian Huygens, that same Huygens who enthusiastically received Roemer's findings, believed light was a wave, a disturbance propagating through some invisible medium, an ether that filled all of space. But Newton's authority in the late 17th and early 18th centuries was enormous, and the particle theory dominated for a long time. It took a young English physician-turned-physicist named Thomas Young to decisively demonstrate the wave nature of light in one of the most elegant experiments ever performed. Young's double-slit experiment, conducted in 1801, is something you've perhaps heard of, and if you haven't, it deserves a moment. Young took a light source, a sunlit pinhole, and let the light fall onto a screen with two very narrow parallel slits cut into it. On the other side of the slits, he placed another screen to catch what came through. If light were made of particles, you'd expect to see two bright stripes on the second screen, one behind each slit. The particles would fly straight through and land in a direct line. Instead, what Young saw was a pattern of many alternating bright and dark stripes spread across the screen. Many stripes, not two. The light coming through one slit had spread out and overlapped with the light coming through the other slit. And where the two overlapping waves lined up crest to crest, they reinforced each other and produced brightness. Where they lined up crest to trough, they canceled each other and produced darkness. This is called interference. It is the signature of waves. Waves do this. Particles don't. Light was a wave. But a wave of what? What was doing the waving? This remained a deep mystery through the early 19th century. The wave camp kept winning experimental victories, better measurements of diffraction, studies of polarization. Léon Foucault's precision measurement of the speed of light in 1850 showing it was slower in water than in air, which the wave theory predicted and the particle theory did not. But the underlying medium remained elusive. The ether was everywhere assumed, but nowhere observed. And then, in the 1860s, a Scottish physicist named James Clerk Maxwell did something that changed everything. James Clerk Maxwell was born in Edinburgh in 1831, the son of a lawyer who also had a keen amateur interest in science. He was one of those people who becomes a great scientist partly because they are constitutionally incapable of accepting a mystery as just a mystery. He needs to understand. He needs to find the underlying structure. He spent years studying electricity and magnetism, two forces that by the mid-19th century were known to be related in some way. Michael Faraday had shown that a moving magnet could generate an electric current, and that an electric current could create a magnetic field. But the relationship between the two forces wasn't yet expressed in precise, unified mathematical language. Maxwell supplied that language. In 1865, he published a dynamical theory of the electromagnetic field, laying out what we now call Maxwell's equations, four compact mathematical expressions that describe, with complete generality, how electric and magnetic fields are generated and how they interact. These equations were beautiful. They still are. But Maxwell noticed something in them that surprised even him. His equations, when combined, predicted the existence of waves. Not sound waves. Not mechanical waves. Electromagnetic waves. Oscillating electric and magnetic fields propagating through space, each one generating the other in an endless cycle. An electric field changing in time creates a magnetic field. A magnetic field changing in time creates an electric field. And so on, rippling outward. And when Maxwell calculated how fast these waves would propagate, he got a number. A very specific number. The speed at which electromagnetic waves would travel through empty space, according to his equations, was determined entirely by two constants that could be measured in an ordinary laboratory: the permittivity of free space and the permeability of free space. Plug them in, do the arithmetic, and you get approximately 299,000 kilometers per second, which was, as Maxwell immediately recognized, very nearly exactly the measured speed of light. He wrote that the coincidence was scarcely deniable and concluded that light itself must be an electromagnetic wave, a transverse oscillation of electric and magnetic fields, rippling through space at the speed his equations predicted. This was one of the most startling unifications in the history of physics. Light, electricity, and magnetism, three seemingly separate things, all reduced to a single underlying phenomenon. Light is what you get when you shake a charge. But there was a problem embedded in Maxwell's equations. A quiet problem that nobody paid much attention to at first. Something that would take 30 more years to become troublesome, and then would eventually require a complete reimagining of space and time to resolve. The problem was this. Maxwell's equations gave you the speed of light as an absolute value. Not the speed relative to something, just the speed. As though it were a fixed number in the universe, independent of how fast you or the light source might be moving. In Newtonian mechanics, speeds add. If you're on a train moving at 60 kilometers per hour and you throw a ball forward at 30, someone standing still on the platform sees that ball moving at 90. Of course they do. That's obvious. That's just how the world works. But Maxwell's equations seem to suggest that light didn't follow this rule. The speed of light, according to his math, was just c, a constant, not relative to anything. Simply the speed at which electromagnetic disturbances propagate, which didn't make sense. Or did it? What was the light propagating relative to? The ether, presumably, the invisible medium. And if you were moving through the ether, light should appear faster or slower depending on your direction of travel, just as a swimmer moving against a current goes slower than a swimmer going with it. So someone needed to measure the difference. To detect Earth's motion through the ether by measuring whether light was slightly faster in one direction versus another. That experiment was carried out in 1887 by an American physicist named Albert Michelson and his collaborator Edward Morley, and its result was one of the most famous non-results in the history of science. Albert Michelson was, in some ways, the opposite of Roemer. Where Roemer stumbled onto his discovery while looking for something else entirely, Michelson was consumed, almost to the point of mania, by the precision measurement of the speed of light. It was the great project of his scientific life, and he returned to it again and again over 4 decades, each time squeezing out a more precise value. He was born in 1852 in what is now Strzałko, Poland, emigrated to the United States as a child, grew up in the rough-and-tumble mining towns of Nevada and California during the gold rush years, and somehow, through sheer determination and the sponsorship of a sympathetic admiral, secured a place at the Naval Academy in Annapolis. There, his gift for precise measurement became apparent early, and he eventually left the Navy to pursue physics full-time. By the mid-1880s, working at what is now Case Western Reserve University in Cleveland, Michelson had already made the most precise measurement of the speed of light in history. But he had a new question. If light travels through the ether, and Earth moves through the ether as it orbits the Sun, shouldn't we be able to detect Earth's motion by measuring a slight difference in the speed of light in different directions? Earth is plowing through the ether at about 30 kilometers per second in its orbit. Light should appear slightly slower when you're measuring it against the ether current than when you're measuring it across the current. He built, with Morley, an interferometer, a device that splits a beam of light in two, sends each half down a different path, and then recombines them. When the two beams recombine, they create an interference pattern, those bright and dark fringes. And if one beam had traveled a slightly longer effective path because it was going against the ether current, the fringe pattern would shift when you rotated the apparatus. The interferometer was mounted on a massive sandstone slab floating in a pool of liquid mercury to isolate it from vibrations. They could rotate it smoothly and watch for any shift in the fringes. The shift they expected was tiny but calculable. Michelson knew exactly how big it should be. They saw nothing. The fringes didn't shift. Not by the expected amount. Not by any amount, really. The speed of light appeared to be the same in every direction, regardless of how the apparatus was oriented. Michelson was, by all accounts, disappointed. He thought he might have made an error. He repeated the experiment. Same result. He tried at different times of year when Earth's orbital velocity pointed in different directions. Still nothing. What the Michelson-Morley experiment told the world was that either the ether didn't exist, or it was dragged along perfectly with Earth in a way that made it undetectable, or there was something deeply wrong with the assumptions behind the whole search. Most physicists in the 1880s and 1890s tried hard not to draw the most radical conclusion. A Dutch physicist named Hendrik Lorentz, and independently the Irish physicist George Fitzgerald, proposed that perhaps moving objects physically contract in the direction of their motion through the ether, just enough to cancel out the effect Michelson was looking for. This was the right mathematical answer, as it would turn out. But they attached it to the wrong explanation. They still believed in the ether. It took an 18-year-old in Zurich, somewhere around 1896, to begin asking the question differently. Not why can't we detect the ether, but what if there is no ether? What if the speed of light is simply the same for everyone, always, in every direction, as a fundamental property of the universe? That teenager was Albert Einstein, and the consequences of his question would turn out to be the most profound restructuring of human understanding since Newton. We'll return to Einstein soon, because his story with light is long and wonderful and worth telling properly. But first, let's come back to Michelson himself, because he didn't stop. You have to appreciate this. The Michelson-Morley experiment is remembered as a famous null result, a negative finding, a thing that didn't happen. But Michelson spent the next 40 years refining the measurement of light speed, not because he was stuck in a rut, but because he believed the number itself was worth knowing with the greatest possible precision. He moved from Cleveland to the University of Chicago, then to a position in California, and in the final years of his life, in the late 1920s, he undertook an extraordinary project. He built a long, evacuated tube, more than a mile long, running through the hills of Pasadena, California, through which he bounced light back and forth between precisely machined mirrors, measuring the time it took with rotating mirror systems of extraordinary delicacy. He died in 1931 before the final results were analyzed, but the data his team collected yielded a value of 299,774 kilometers per second, accurate to within a few dozen parts per million of the true value. The man spent his entire career chasing this number, refining it, squeezing another decimal place out of it, and in doing so built the experimental tradition of precision optical measurement that eventually made lasers and interferometers and fiber optics possible. His obsession was not wasted time. It was infrastructure. The value of the speed of light is now known with absurd precision, 299,792.458 kilometers per second exactly, and I do mean exactly. In 1983, the international scientific community made a remarkable decision. They defined the meter in terms of the speed of light and a specific number of oscillations of a cesium atom. The speed of light was no longer a measured quantity. It was a defined constant. The universe had given us something so reliable, so invariant, that we built our system of measurement around it. That's how much we trust it. But to understand why it's invariant, why every observer in every state of motion measures the same value for the speed of light, we have to return to that young man in Zurich, now a young man in Bern, working as a patent examiner, who had been sitting with a question for nearly a decade. Albert Einstein submitted the paper that would become special relativity in June 1905. He was 26 years old. He was working as a technical expert, third class at the Swiss Patent Office in Bern, spending his days evaluating applications for mechanical devices, and his evenings and weekend mornings thinking about physics. The paper's title was, in German, On the Electrodynamics of Moving Bodies, which does not sound like one of the most revolutionary documents in human history. But it was. Einstein began with two postulates. Not results. Not theorems. Postulates. Things he was assuming to be true, and then asking what would follow if they were. The first postulate was Galileo's old principle of relativity, updated and extended. The laws of physics are the same for all observers in uniform motion, that is, for anyone moving at constant velocity, not accelerating. There is no experiment you can perform inside a smoothly moving spaceship, with the windows closed, that will tell you whether you are moving or standing still. Galileo had said this for mechanics. Einstein extended it to all of physics, including electromagnetism. The second postulate was the strange one. The speed of light in vacuum is the same for all observers, regardless of the motion of the light source or the observer. If you're moving toward a light source at half the speed of light, you don't measure the light coming toward you at 1.5 times the speed of light. You measure it at c, the full unchanged value. just like everyone else, just like someone standing still. This sounds like a contradiction. It feels like a contradiction. If you and I are both chasing a light beam, and you're running faster than I am, shouldn't you see the light moving away from you more slowly than I see it moving away from me? Einstein said no. And then he asked, if this is true, if we're going to take both postulates seriously, what follows? What follows is that our assumptions about time and space, assumptions so deep we've never even noticed we were making them, turn out to be wrong. The first thing that breaks is simultaneity. The idea that two events happening at the same moment for one observer must happen at the same moment for all observers. Einstein showed, with a beautifully simple thought experiment, that this isn't true. Picture two lightning bolts striking the front and back of a moving train at the same moment, as judged by someone standing on the platform exactly midway between the two strike points. Both lightning bolts hit at the same time, from the platform observer's perspective. He sees both flashes arrive at his eyes simultaneously, because he's equidistant from both, and light travels at the same speed in all directions. But now consider the passenger sitting in the exact center of the train. She's also equidistant from both ends of the train. But the train is moving forward, toward the front lightning strike and away from the rear one. So as the light from both strikes travels inward toward her, she's moving slightly toward the front flash and away from the back flash. The front flash reaches her first. Now, if the speed of light is the same for her as for the platform observer, same speed, no exceptions, then she can't say the front flash arrived first because I was moving toward it. In her reference frame, she's stationary. Light traveled the same speed from both ends. Front flash arrived first. Therefore, from her perspective, the front lightning bolt struck before the rear one. Two events that are simultaneous for one observer are not simultaneous for another. There is no universal now. There is no single moment that is the present moment for everyone in the universe at once. What is now depends on where you are and how fast you're moving. Different observers slice up space-time into past, present, and future differently, and all of those slicings are equally valid. Just sit with that for a moment. That's not a human perception problem. That's not relativity in the everyday sense of it, depends on your perspective. It's a physical fact about the structure of the universe. And once simultaneity goes, time itself starts behaving in ways that seem impossible. Moving clocks run slow, not because they're broken, not because of some mechanical effect of motion, because time itself, for a moving observer, passes at a different rate than for a stationary one. This is called time dilation, and it's been measured, not just theoretically worked out, measured in laboratories, on airplanes, on GPS satellites. The way to understand it is through Einstein's own type of thought experiment. Simple, physical, unavoidable. Imagine a clock made of nothing but two mirrors facing each other and a light pulse bouncing between them. Each round trip of the light pulse is one tick of the clock. Simple, reliable. The time per tick is just twice the distance between the mirrors divided by the speed of light. Now put this clock on a moving train, oriented vertically, one mirror on the floor, one on the ceiling. The passenger on the train sees the light pulse go straight up and straight back down. Tick, tick, tick. From the platform, you see something different. The train is moving horizontally. So the light pulse, while bouncing between the mirrors, is also traveling horizontally along with the train. From your perspective, the light traces a diagonal path. It moves up and to the right, bounces, comes down and to the right. A zigzag. That diagonal path is longer than the straight vertical path the passenger sees. It has to be. The geometry forces it. The light is covering more distance per tick, as you see it. But the speed of light is the same for both of you. You can't have light covering more distance at the same speed without taking more time. So each tick of the moving clock, as seen from the platform, takes longer than each tick as seen by the passenger. The moving clock runs slow. And because everything in the moving frame, biological aging, chemical reactions, radioactive decay, the spinning of electrons, runs on the same underlying physics, it all slows down together. The passenger doesn't experience anything unusual. She doesn't feel herself moving in slow motion. But if she steps off the train and compares clocks with the platform observer, her clock shows less elapsed time. She has genuinely aged less. This is not science fiction. Muons are subatomic particles created high in the atmosphere when cosmic rays collide with air molecules. They decay very quickly. In the lab, a muon lives only about 2.2 microseconds before disintegrating. At the speed they travel coming down from the atmosphere, they should, by Newtonian calculation, decay before they reach the ground. But they don't. We detect them at the surface all the time. The reason is time dilation. Moving at nearly the speed of light, their internal clocks run slow relative to us, and they live long enough to reach the ground. We catch them. We count them. The numbers match Einstein's predictions with high precision. This isn't a metaphor. It's muons, real particles, actually living longer because they're moving fast. And it doesn't stop at time. Space itself is affected too. A moving object is shorter in the direction of motion than the same object at rest. Again, not because it's being squeezed by some force, but because the geometry of space-time works that way. Length contracts. The faster you move, the shorter you appear to a stationary observer along the direction of travel. And there's another consequence, perhaps the most famous equation in all of physics, which Einstein derived from the same two postulates later that year. EMC superscript 2. Energy and mass are equivalent. They're the same thing, viewed from different angles. A given mass is a certain amount of energy, frozen, stored. And the conversion factor between them is c superscript 2, the speed of light squared, which is an enormous number. A very small mass corresponds to an almost unimaginable amount of energy. This equation came not from experiment or observation, but from following the logic of the two postulates to their conclusions. It was a mathematical consequence of taking the constancy of the speed of light seriously. And it turned out to describe, precisely, the energy released in nuclear reactions. The sun converts about 600 million tons of hydrogen into helium every second, and in doing so, it loses about 4 million tons of mass, converted to energy, radiated outward as sunlight. The light that settles on your skin on a warm afternoon is the energy of mass that used to be part of the sun, transformed via the most famous equation in human history, then traveling 150 million kilometers in 8 minutes to find you. But there was something missing from Einstein's special theory of relativity, and he knew it immediately. Special relativity dealt beautifully with observers moving at constant velocity, but it said nothing about acceleration, nothing about gravity. And gravity was obviously everywhere, the dominant force shaping the large-scale universe, the thing that holds planets in orbit and keeps you from floating off your bed. Newton's theory of gravity was still in place, still wildly successful, still the tool engineers and astronomers used to calculate orbits and trajectories. But it was incompatible with special relativity. In Newton's gravity, gravitational effects propagate instantaneously across any distance. The sun pulls on Earth right now, at this moment, across 150 million kilometers, with no delay. But special relativity said nothing could propagate faster than light. Something had to give. Einstein spent the next 10 years working on this problem. He later called it the hardest thinking of his life, far harder than special relativity, which had come to him relatively quickly. The general theory of relativity, the extension that would encompass gravity and acceleration, required mathematical tools he didn't initially possess, conceptual leaps that nearly broke him, and more than one dead end that he followed for years before recognizing his mistake. But the key insight, the thing he later called the happiest thought of his life, came to him in 1907, just 2 years after special relativity. He imagined a man falling off a building. This is morbid as a thought experiment goes. But here's what struck Einstein. A person in free fall feels no weight. If you dropped everything you were holding, let go completely, you'd feel weightless. The floor wouldn't push up on your feet. Gravity would still be there, acting on every atom of your body. But because every atom is falling together, there's no sensation of weight, no differential force. It would feel, for those brief seconds, like floating in empty space. Einstein realized something profound in this image. Freefall and weightlessness are locally indistinguishable. You can't tell, from inside a freely falling elevator, whether you're falling in a gravitational field or drifting in empty space far from any mass. The physics feels the same. And by the same logic, you can't tell, from inside an accelerating rocket in empty space, whether you're accelerating or simply sitting still in a gravitational field. If the rocket accelerates at 9.8 meters per second squared, exactly the rate at which Earth's gravity accelerates things. Everything inside it will feel exactly like Earth's gravity. Drop something, it falls. Stand on a scale, it reads your normal weight. There's no local experiment you can do that tells you which situation you're in. This is the equivalence principle, and from it, Einstein could immediately draw remarkable conclusions before he even had the full mathematical theory. If you're in an accelerating rocket and you shine a flashlight sideways across the room, the light will appear to curve downward, because while the light is traveling across the room, the rocket is accelerating upward, so the floor rises to meet the light. The beam appears to bend toward the floor. But if acceleration and gravity are equivalent, then gravity must also bend light. Light bends in a gravitational field. A beam of starlight passing close to the sun should be deflected by the sun's gravity. The star should appear to be in a slightly different position than it would be if the sun weren't there. And Einstein, working through the mathematics carefully, calculated the exact amount of bending, arriving, by 1915 and the completion of general relativity, at a prediction of 1.75 arcseconds for a star at the edge of the sun's disk. An arcsecond is 1/3600th of a degree. It's a tiny angle, but it's measurable. If you could see stars near the sun, which you normally can't, because the sun's glare drowns them out, and if you could compare their apparent positions when the sun is nearby versus when it isn't, you'd see the shift. You can see stars near the sun during a total solar eclipse. When the moon blocks the sun's disk for a few minutes, the sky goes dark enough to photograph stars in the vicinity of the sun. A British astrophysicist named Arthur Eddington organized 2 expeditions to observe the solar eclipse of May 29, 1919, one to the island of Principe off the west coast of Africa and one to Sobral in Brazil. He had been one of the few British scientists who had kept up with German physics during the First World War, and he was determined to test Einstein's prediction. The eclipse observations were difficult. Principe was cloudy for most of totality. Some of the Sobral plates were distorted by heat, but enough data survived. And when Eddington analyzed the plate measurements and announced the results at a joint meeting of the Royal Society and Royal Astronomical Society in November 1919, the answer was, the stars near the sun appeared shifted by approximately 1.75 arcseconds. Exactly as Einstein had predicted. The Times of London ran the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." And Albert Einstein, overnight, became the most famous scientist in the world. The significance wasn't just that the prediction was confirmed. It was what the confirmation meant. Newton's gravity had stood for 2.5 centuries as the unchallenged description of gravitational force. And now here was something deeper. A theory in which gravity wasn't a force at all, but a curvature of space-time, caused by the presence of mass and energy, with objects and light simply following the natural pathways through that curved geometry. Gravity isn't a pull. It's a geometry. Mass tells space-time how to curve. Space-time tells mass how to move. And light, having no mass, still bends, because it follows the curvature of space-time, and space-time curves wherever mass is present. The universe was not the one Newton had described. It was the one Einstein described. And the speed of light, c, that strange constant hiding in Maxwell's equations, was the very number that determined the relationship between mass and energy, the speed limit of causality, the constant at the heart of the curvature of space-time. Light was not incidental to this picture. Light was, in some sense, built into the structure of the universe. Now let's slow down a little. Let the history settle. We've followed light's story from Galileo on the hillside with his lantern to old Romer watching Jupiter's moons, from Maxwell unifying electricity and magnetism to Einstein finding that time dilates and space contracts and gravity curves the path of a beam of starlight. That's 3.5 centuries of physics, and we've moved through it fairly quickly. But there's a second story running alongside this one, a parallel thread, and it's the story of what the speed of light, this strange, constant, absolute value, actually did to our understanding of space and time. Not just theoretically, but physically, concretely, in ways that the everyday world eventually had to reckon with. Because here's the thing about the speed of light that people often miss when they first encounter relativity. It's not just a speed limit. It's a structural constant. It shows up everywhere, in deep and unexpected ways. It's the number that determines how much energy is locked inside a given amount of mass. It's the number that determines how much gravity slows time. It's the number that limits how quickly information can travel from one point in the universe to another. And it's the number that defined, for decades, one of the most important engineering problems in modern technology. The problem is this: when you need to know very precisely what time it is, and you need to know it in a way that stays consistent across distances, light's travel time becomes a practical engineering constraint, not just a theoretical curiosity. And nowhere is this more elegantly visible than in GPS. The Global Positioning System consists of 24 satellites plus spares orbiting Earth in medium orbit, each carrying extremely precise atomic clocks and continuously broadcasting signals. When your phone receives signals from several of these satellites simultaneously, it compares the arrival times of the signals and calculates how far away each satellite is, because it knows how fast the signals travel at the speed of light, and it can measure how long each signal took to arrive. With distances to 4 or more satellites, it can pinpoint your position in 3 dimensions. The entire system depends on clocks that agree. If the satellite clocks drift relative to each other, or relative to clocks on the ground, the position calculations go wrong. An error of 1 microsecond, 1/1,000,000th of a second, in the timing corresponds to a position error of about 300 meters. The system uses atomic clocks accurate to within a few nanoseconds per day. But here's where Einstein shows up, in a very concrete and expensive way. The GPS satellites are moving. They orbit at about 14,000 kilometers per hour. According to special relativity, moving clocks run slow, so the satellite clocks tick slightly slower than stationary clocks on the ground. The effect works out to about 7 microseconds per day of slowing. But the satellites are also higher up in Earth's gravitational field than clocks on the surface. According to general relativity, clocks in weaker gravitational fields run faster than clocks in stronger fields. A consequence of the equivalence principle. If gravity and acceleration are equivalent, and accelerating rocket clocks run in a specific way, then gravitational fields must also affect clock rates. The higher you are above Earth, the weaker the gravity, the faster your clock ticks relative to a clock on the surface. This effect works out to about 45 microseconds per day of speeding up. The net effect: GPS satellite clocks run fast by about 38 microseconds per day relative to ground clocks. 38 microseconds per day doesn't sound like much, but at the speed of light, 38 microseconds corresponds to about 11 kilometers. If you didn't correct for relativistic effects, the GPS system would accumulate an 11-kilometer position error every single day. Within a few days, it would be useless for navigation. So the satellite clocks are deliberately set to tick slightly slow before launch, compensating in advance for the relativistic effects they'll experience in orbit. The engineers who designed the system had to incorporate both special and general relativity to make the system work. Every time you use a map application to find your way somewhere, you are relying on Einstein's theories of relativity to be correct. This is not metaphorical. It's an engineering fact, baked into the orbital parameters and clock calibrations of the satellites. The useless philosophical question of whether time is absolute, a question that seemed like pure abstraction when Einstein posed it in 1905, turned out to have a very practical answer. Time is not absolute, and the correction you have to apply to account for that non-absoluteness determines whether your navigation system tells you to turn left onto the right street or drives you into a lake. But there's more. Because the constancy of the speed of light isn't just useful for GPS. It's the backbone of the entire modern communications infrastructure. Fiber optic cables carry the internet. Long, thin strands of glass, bundled in cables that crisscross the ocean floor and thread through conduits under city streets, transmitting information encoded as pulses of laser light. The light travels through the glass at about 2/3 the speed it would travel in vacuum, around 200,000 kilometers per second, and that speed is precisely known and precisely engineered. Every time you send an email, stream a video, make a phone call over the internet, the information is being carried as pulses of light racing down glass fibers. The speed of those pulses determines how quickly data can travel from one continent to another. The latency, the delay, of an internet connection between New York and London is fundamentally limited by the time it takes light to travel approximately 6,000 kilometers of fiber, taking a slightly longer route than the straight-line geographic distance. The delay is roughly 70 milliseconds. You can't make it faster without violating the laws of physics. Financial markets worry about this. High-frequency traders have actually laid new undersea cables taking the most geometrically direct routes between financial centers, shaving milliseconds off their connection times. They've built data centers physically close to the stock exchange servers to reduce the fraction of a millisecond it takes for their signals to travel. The speed of light is a business problem, a competitive constraint, a source of real financial advantage to those who can engineer their systems to account for it most cleverly. Ole Romer, watching the eclipses of Io with patient care in the 1670s, was measuring the same constant that hedge funds now pay tens of millions of dollars to be on the right side of. The world is strange. Let's talk about lasers. Because lasers are perhaps the most direct technological embodiment of everything we understand about light, and they're also everywhere. In your home, in hospitals, in factories, in the fiber optic cables we just discussed, in the GPS satellites we talked about before that. The word laser is an acronym: light amplification by stimulated emission of radiation. The key word is stimulated, and to understand it, you need to know a little about what Einstein was doing in 1917. In that year, 12 years after his miracle year and 8 years before he would complete general relativity, Einstein published a paper on the interaction of light and matter in which he described 3 processes: absorption, spontaneous emission, and stimulated emission. Absorption you know intuitively. A material absorbs light when the photons, the individual packets of light energy, transfer their energy to electrons in the material, kicking those electrons up to higher energy states. Spontaneous emission is what happens when that excited electron eventually drops back down to its lower energy state on its own, releasing a photon. This is how most light sources work. The electrons in the filament of an incandescent bulb are constantly being excited by electrical energy and constantly dropping back down, releasing photons in random directions, at random times, in a jumble of phases. The result is incoherent light, bright but scattered, spreading in all directions. Stimulated emission is stranger. Einstein predicted that if a photon of exactly the right energy passes near an already excited electron, it can trigger that electron to drop back down immediately, releasing another photon. And here's the remarkable part. The new photon is identical to the incoming one. Same direction, same phase, same energy, same wavelength. 1 photon in, 2 photons out, both perfectly matched. If you have a medium full of excited atoms, 1 photon passing through can trigger a cascade. 1 becomes 2, 2 become 4, 4 become 8. Each new photon identical to all the others, all marching in lockstep. A coherent beam. All the light in phase, all traveling in the same direction, all at the same wavelength. That's a laser. Einstein predicted the theoretical possibility of stimulated emission in 1917. The first working laser wasn't built until 1960, when Theodore Maiman at Hughes Research Laboratories in Malibu, California, flashed a bright light through a synthetic ruby crystal and produced a brief pulse of intense, coherent red light. People at the time called it a solution in search of a problem. They couldn't immediately see what such a precise, intense, concentrated beam of light would be good for. They were wrong, of course. Lasers have become so woven into modern life that enumerating their applications starts to feel like listing the uses of electricity. Laser printers, laser eye surgery, laser cutting and welding in manufacturing, barcode scanners, the CD and DVD players of an earlier era, the LiDAR sensors in autonomous vehicles, laser rangefinders in construction, the fiber optic communication systems we've already discussed, laser pointers in every conference room in the world. And then there's one application that stands apart. An application so audacious that when it was first seriously proposed, many physicists thought it was impossible, and when it was finally achieved, it was recognized with a Nobel Prize and called one of the greatest measurement achievements in the history of human civilization. LIGO. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. There are 2 of them, one in Hanford, Washington, and one in Livingston, Louisiana, and they are, in some sense, the most sensitive measuring instruments ever built by human beings. Each LIGO detector is shaped like an L. Two arms, each 4 kilometers long, perpendicular to each other. A laser beam is split at the corner of the L and sent down each arm. At the end of each arm, a mirror reflects the beam back. The two beams are recombined at the corner, where they interfere with each other, producing a pattern that is exquisitely sensitive to any difference in the lengths of the two arms. The purpose of this machine is to detect gravitational waves, ripples in space-time itself, predicted by Einstein's general theory of relativity, but not observed until 2015, exactly a century after he completed the theory. Gravitational waves are produced by massive objects undergoing rapid acceleration, two neutron stars spiraling into each other, two black holes merging, a supernova collapsing. The waves spread outward at the speed of light, compressing space in one direction while stretching it in the perpendicular direction. When such a wave passes through LIGO, it stretches one arm and compresses the other, and the laser interference pattern changes accordingly. How much do the arms change in length? This is where the numbers become genuinely mind-bending. LIGO can detect a change in arm length of approximately 1,000th of the diameter of a proton. A proton is about 0.85 femtometers across. 1 femtometer is 10 superscript 1 meters. 1,000th of that is 10 superscript 1 meters. The 4-kilometer arms of LIGO change length by 10 superscript 1 meters when a gravitational wave passes through, and LIGO detects it. That's like measuring the distance from Earth to the nearest star and being sensitive to a change of one atom's width. The precision required is so extreme that LIGO must contend with noise sources that most measurement systems can simply ignore. The thermal motion of atoms in the mirrors, quantum fluctuations of the light itself, seismic rumbles from trucks driving on roads miles away. They use elaborate isolation systems, suspended mirrors hanging from chains of pendulums, active feedback systems that counteract ground motion, and a technique called quantum squeezing, in which the quantum noise of the light is manipulated using entangled photon states to push the uncertainty out of the measurement channel and into one they don't care about. They are engineering around the Heisenberg uncertainty principle. On September 14, 2015, both LIGO detectors simultaneously registered a signal. The signal lasted about 0.2 seconds. It swept upward in frequency from about 35 Hz to 150 Hz, a chirp in the audio range. When converted to sound, it makes a brief rising tone, a fraction of a second long, that you might not even notice if it played in a noisy room. That signal came from two black holes, each about 30 times the mass of the Sun, spiraling together and merging approximately 1.3 billion light-years away. In the final fraction of a second before merger, the system was radiating more power than all the stars in the observable universe combined. And the tiny ripple in space-time that reached Earth, 1.3 billion years later, having traveled 1.3 billion light-years, was 10 superscript 1 meters in its effect on LIGO's arms. The measurement matched Einstein's equations to extraordinary precision. The exact shape of the signal, the way it swept upward, the rate of the frequency change, the loudness at each moment. All of it followed the mathematics of general relativity exactly. A century after Einstein wrote down his field equations, in November 1915, we detected a gravitational wave that had been traveling since before there was complex life on Earth. And we used lasers and quantum optics and mirrors so smooth, they can detect atomic-scale vibrations to match it to predictions made with pencil and mathematics in Berlin during the First World War. Sometimes physics feels almost impossible to believe. But let me back up and take a slower path through one part of this story that deserves more time. Because I've been moving quickly through a century of physics, and there's something I want to linger on. The story of how the speed of light moved from philosophical curiosity measured by a Dane watching Jupiter's moons to foundational constant in the technology keeping your phone working is not just a story of equations and experiments. It's a story of argument, of people not quite believing what other people were telling them, of ideas that seemed, for decades, like they belonged only to the domain of the abstract, questions with no practical consequence whatsoever, turning out, eventually, to be the foundations of everything. Think about what Maxwell's achievement actually meant when it was first announced. In 1865, He published his equations unifying electricity and magnetism and light, and he predicted electromagnetic waves that should propagate through space at a calculable speed. This was purely theoretical. No one had ever transmitted or received an electromagnetic wave deliberately. The radio didn't exist. The telephone didn't exist. Television, radar, microwave communication. All of this was science fiction of a kind that hadn't even been written yet. It wasn't until 1888, 23 years after Maxwell's equations, that a German physicist named Heinrich Hertz actually generated and detected electromagnetic waves in a laboratory. He set up an oscillating circuit on one side of his lab that generated radio waves, and a detector on the other side that received them. The waves crossed the lab. They reflected off walls. They diffracted around objects. They behaved exactly as Maxwell's equations said they should. Hertz reportedly said, when asked about the practical implications of his discovery, "It's of no use whatsoever. This is just an experiment that proves Maestro Maxwell was right. We just have these mysterious electromagnetic waves that we cannot see with the naked eye." And when pressed further, he reportedly added, "I do not think that the wireless waves I have discovered will have any practical application." He was, needless to say, catastrophically wrong about that. Within a decade, Guglielmo Marconi had built wireless telegraphy systems. Within 2 decades, radio signals were being used for long-distance communication. Within 50 years, electromagnetic waves were the backbone of global communication, radio, television, radar, satellite transmission. All of it flowing directly from Maxwell's theoretical work. All of it traveling at the speed of light. All of it, ultimately, made possible by the fact that electricity and magnetism and light are the same thing, expressed through his 4 equations. There is a lesson here that physicists return to again and again. The most abstract and apparently useless theoretical work has a habit of becoming, given enough time, the most practically transformative. Einstein's special relativity, published in 1905, seemed to most working engineers and scientists of the time like the most rarefied possible abstraction. Time dilation and length contraction were interesting, philosophically unsettling, even, but they dealt with conditions so extreme velocities approaching the speed of light that they seemed irrelevant to any practical concern. Who was going to be moving at a significant fraction of the speed of light? Nobody. The corrections were too small to matter in any real-world context. And yet, a century later, GPS satellites needed relativistic corrections to work at all. The corrections were small, a few tens of microseconds per day, but in a system that depends on nanosecond-level timing precision, a few tens of microseconds is a catastrophic error. The engineers who designed GPS had to understand and account for relativistic effects. They had to build Einstein's abstract time dilation mathematics into the firmware of orbiting satellites. The gap between abstract philosophical argument between physicists and essential feature of commercial satellite navigation turned out to be just about a century. That's a long time in human terms, but it's an eye blink in the history of human understanding, and the pattern repeats over and over throughout the history of physics. Let's spend a moment with the person who, more than anyone, bridges the philosophical and the practical in the story of light. Not Einstein, though he certainly bridges them too. I mean Albert Michelson. We've already met Michelson, the meticulous measurer, the man who spent 40 years refining the value of C, the person whose 1887 experiment with Morley turned up nothing when it was supposed to turn up a detectable shift in light speed due to Earth's motion through the ether. We've acknowledged that his null result was historically important, but I want to give you a fuller picture of the man, because he's one of those figures whose character is inseparable from his contribution. Michelson was consumed by precision in a way that went beyond professional dedication. His colleagues sometimes found it disconcerting. He once reportedly said that the speed of light was the most beautiful measurement in all of physics, not because of what it told you about the universe, but because of the measurement itself, the act of measuring it, the design of the instrument, the control of the errors, the refinement of the technique. He was also, by many accounts, difficult, taciturn, perfectionist, unable to delegate because nobody else could meet his standards. His first marriage failed partly because of his all-consuming dedication to his work. He was cold to colleagues who he felt weren't serious enough. He had a reputation for dismissing theoretical work as merely mathematical. which makes it somewhat ironic that his null result became the experimental linchpin of the most mathematical and theoretical revolution in the history of physics. But that's often how it goes. The people who build the instruments that change science don't always understand, or even particularly care about, the theoretical consequences of what they've measured. Michelson wanted to measure the speed of light and detect Earth's motion through the ether. He failed at the second, and in failing, he handed Einstein and Lorentz and Fitzgerald the experimental fact that their theories had to explain. His last major project, the one he undertook in his 70s, speaks to something deep in his character. He built a tube over a mile long, evacuated of air, mounted carefully in the hills near Pasadena, specifically to remove the variation in light speed caused by air currents and weather. He could have simply made more careful measurements with existing equipment. But Michelson wanted the ideal measurement, the one where you'd controlled for every possible source of error, the one that would be done, in some final sense, right. He died in 1931 before the results were fully analyzed. But the data he'd gathered was processed posthumously by his colleagues, and it gave a value within a few parts per million of the accepted value today. In his final decade, Michelson had a habit of remarking that the future of physics would probably be found in the 6th decimal place, by which he meant, the big discoveries are largely done. What remains is to refine our measurements. He said something similar to what Lord Kelvin had said in the 1890s, when he commented that physics was essentially complete. Both of them were spectacularly, beautifully wrong. What was waiting in the 6th decimal place, in the refinements, in the precision measurements, in the careful accounting for small discrepancies, was quantum mechanics and general relativity and the entire revolution of 20th century physics. The moral, I suppose, is that the universe always has more in store. The it's nearly done feeling in physics has, historically, been reliable only as a signal that something extraordinary is about to happen. Let's linger now on one of the strangest aspects of the speed of light, the one that still stops physicists in their tracks when they think about it carefully. Light, in vacuum, travels at 299,792.458 kilometers per second. Not approximately. Not about. Exactly. This is now definitionally exact, because we have defined the meter in terms of the second and the speed of light. But the question of why light travels at this particular speed, and not twice as fast, or half as fast, or any other value, doesn't have a satisfying answer. It's what physicists call a given, a constant of nature, something the universe has, as it were, decided. Now, c is not entirely arbitrary in the sense that other aspects of physics depend on it in interconnected ways. If c were different, the relationship between energy and mass would be different since EMC superscript 2. The size of atoms would be different since electromagnetic forces, which hold atoms together, propagate at c. The rate of nuclear reactions would be different. The universe would be, fundamentally, a different place, with different chemistry and different physics at every scale. So c isn't arbitrary in the sense that you could just dial it up or down without consequences. Change c and you change everything. But why is it the value it is, rather than some other value? We don't know. It's a measured constant, not a derived one. We measure it. We use it. We can't derive it from more fundamental principles. This is actually a deep question that sits at the frontier of current physics. Are the constants of nature, c, the gravitational constant g, Planck's constant h, the fine structure constant alpha, fixed forever by some deeper logic we don't yet understand? Or are they, in some sense, contingent? Could they have been different? In different regions of the universe? At different times in its history? These are not idle philosophical questions. There's serious theoretical work exploring whether the constants of nature might vary on cosmological timescales or across very large spatial scales. The evidence so far is that they don't. Measurements of the fine structure constant using light from quasars billions of light years away, and hence from billions of years ago, show no significant variation. But the question is still genuinely open in some respects. What we can say is this: the speed of light, as a feature of the universe, is woven into the fabric of reality in a way that goes far deeper than a simple number on a chart. It determines the structure of spacetime. It sets the rate at which cause can influence effect. It is the conversion factor between mass and energy. It is the frequency at which Maxwell's electromagnetic waves propagate. It is the speed at which gravitational waves travel. And it is, in the modern definition, a fixed point around which our entire system of units is organized. In 1983, the General Conference on Weights and Measures formally defined the meter as the distance light travels in 1299, 792, for 58 of a second. At that moment, the speed of light stopped being a measured quantity and became a defined quantity. We chose to define our unit of length such that c has exactly that value. We set it in stone, or rather, in the International System of Units. This is a philosophical choice of some elegance. We're essentially saying, we trust the speed of light so completely, we're so confident it's invariant and universal, that we'd rather define our measurement system around it than keep measuring it. It's the most reliable constant we know. Let's make it the foundation. And that's a remarkable testament to 3.5 centuries of measurement, from Galileo's unsuccessful hillside experiment to Michelson's mile-long evacuated tube to the quantum optical precision measurements of the late 20th century. The universe gave us a number. We studied it for centuries, and eventually we trusted it enough to build our whole measurement system on it. There is another figure I haven't mentioned yet who deserves a place in this story, and whose work represents one of the most satisfying pivot points from abstract theory of light to technology in your hand. His name is Theodore Maiman, and we mentioned him briefly when we discussed lasers. But let's linger on the moment. Maiman was working at Hughes Research Laboratories in Malibu, California, in 1960. He was 32 years old. He was trying to build a device that Einstein had theoretically described in 1917, a machine that would exploit stimulated emission to produce coherent, monochromatic light. A laser. There was significant competition. Several teams at major universities and research labs, including MIT and Bell Labs, were working on the same problem. The scientific community expected Bell Labs, with its vast resources and brilliant staff, including some of the people who had invented the transistor, to win the race. Maiman worked alone, essentially. He used a synthetic ruby crystal as his lasing medium and a powerful flash lamp, the kind used in photography studios, wrapped around the crystal to excite the atoms. His boss at Hughes thought the ruby approach was a dead end and told Maiman as much. Most of the scientific community agreed. Other approaches seemed more promising. On May 16, 1960, Maiman fired the flash lamp, and the ruby crystal emitted a brief, intense pulse of deep red laser light, the first laser pulse ever produced. Maiman submitted his results to Physical Review Letters, the premier American physics journal. The editors rejected the paper, suggesting it was not sufficiently novel. This rejection is now considered one of the more embarrassing decisions in the history of scientific publishing. He published in Nature instead, where the result was recognized immediately for what it was. The demonstration came so quickly after the theoretical groundwork that many scientists who heard about it initially didn't believe it. The laser, described theoretically by Einstein in 1917, realized experimentally by Maiman in 1960, had gone from idea to working device in 43 years. And then, as with Hertz's radio waves, the practical applications exploded in ways nobody initially foresaw. Maiman's laser could precisely read out the tiny variations on a spinning disk, the principle behind CD players. A slightly different configuration could write and read patterns in magnetic material, the principle behind hard drives. It could be coupled into glass fibers to carry information at the speed of light over enormous distances. It could be tuned to extremely precise frequencies and used to trap atoms, leading to atomic clocks of extraordinary accuracy. It could be used in interferometers to measure gravitational waves from merging black holes. From a flash lamp wrapped around a pink crystal in Malibu in 1960, to the apparatus at LIGO detecting 10 superscript 1 meter displacements in 2015. That's 55 years. And it all runs on stimulated emission, the quantum mechanical process Einstein described in an almost entirely theoretical 1917 paper that was, at the time, of no practical consequence whatsoever. This keeps happening. The purely theoretical, no practical consequences work keeps becoming the foundation of the next century's technology. And the speed of light keeps showing up at the center of it all. Let me take you into one more corner of this story, one that connects the very abstract to the very everyday in a way I find genuinely moving. Atomic clocks. We mention these in the context of GPS, but they deserve a fuller treatment, because they represent the most direct expression in physical hardware of everything we've learned about the quantum nature of light and matter. An atomic clock works by exploiting the quantum mechanical behavior of atoms. When an electron in an atom transitions between two energy levels, it absorbs or emits a photon, a particle of light, at a very specific frequency. That frequency is extraordinarily stable. It doesn't change with temperature or pressure or age. It doesn't drift over time. It is a fundamental property of that particular atomic transition, set by quantum mechanics, invariant throughout the observable universe. The cesium-133 atom has a particular transition between two very closely spaced energy states of its ground state electrons, called the hyperfine transition, that oscillates at exactly 9,192,631,770 cycles per second. Not approximately, not about. This number is now the definition of the second. 1 second is 9,192,631,770 oscillations of the cesium-133 hyperfine transition. A cesium atomic clock works by generating microwave radiation at this precise frequency, using it to drive the cesium atoms and counting the oscillations. The best cesium clocks are accurate to about 1 second in 300 million years. If you had started one at the moment the dinosaurs went extinct, 66 million years ago, it would still be accurate today, having drifted by less than a quarter of a second in all that time. But cesium isn't even the current standard. The best modern atomic clocks use optical transitions, not microwave ones, in atoms like strontium or ytterbium. Optical frequencies are hundreds of thousands of times higher than microwave frequencies, so you can divide time into finer slices, and the clocks are correspondingly more precise. The best optical lattice clocks, as of the mid-2020s, are accurate to about 1 second in 15 billion years, longer than the current age of the universe. If one had started at the Big Bang, it would still be on time. These clocks are so precise that they can measure the gravitational time dilation between different floors of a building. The clock on the second floor of a building ticks measurably faster than the clock on the first floor because it's slightly further from Earth's center and experiences slightly weaker gravity. The effect is tiny, a few hundred billionths of a second per year for a height difference of 1 meter, but modern optical clocks can measure it. Einstein predicted this in 1907. We can now measure it on the scale of a single story in an office building. And these extremely precise clocks are becoming more and more important for navigation, for telecommunications timing, for fundamental physics research, for geodesy, the study of Earth's shape and gravitational field. Future versions may be accurate enough to detect gravitational waves all by themselves, using a network of synchronized atomic clocks that would sense the tiny timing fluctuations as space-time ripples pass through. We have built our perception of time around the quantum mechanical behavior of atoms. We have defined the second itself in terms of light, because the hyperfine transition of cesium is mediated by microwave photons. Our deepest and most reliable way of measuring duration is based on the interaction of light and matter, governed by quantum rules discovered in the 20th century by people who were, at the time, mostly just trying to understand. And this brings me to something I want to say plainly, even if it takes a moment to settle. The history of our understanding of the speed of light is not, ultimately, a story about one number. It's a story about what happens when human beings refuse to accept that's just how it is as a satisfying answer. About what happens when someone, a Romer, a Michelson, a Maxwell, an Einstein, insists on asking the next question even when the current question seems closed. Romer didn't need to know why the eclipses of Io arrived late. He just observed that they did, and he followed the logic to its conclusion. Light takes time. That was enough. That was, in fact, everything. It opened the door to everything that followed. Michelson didn't need to know why he couldn't detect Earth's motion through the ether. He just measured that he couldn't, with increasing precision, and reported the result honestly. He didn't like the result. It wasn't what he'd been looking for. But the data was the data. Maxwell didn't know he was describing light when he wrote down his equations for electricity and magnetism. He was just trying to describe electricity and magnetism. And there it was, hidden inside the mathematics. The speed of light, falling out of the algebra like a surprise. And Einstein didn't know, in 1905, that his two-postulate theory of special relativity would eventually be required for GPS to work. He was 26 years old, working in a patent office, thinking about what it would mean if the speed of light really were the same for everyone. He followed the logic. He accepted the strange consequences: time dilation, length contraction, the relativity of simultaneity, the equivalence of mass and energy. He didn't try to make the consequences more comfortable. He trusted the math. This is the character of physics at its best. Not comfort, not intuition. Trust in the structure, wherever it leads, even when it leads somewhere disorienting. And then patience, sometimes decades or centuries of patience, while the rest of the world catches up to what the mathematics already knew. We have spent a long time now moving through the story of light, its speed, its nature, its relationship to space and time, its role in the infrastructure of modern life. And I want to slow down further here, near the end, and sit with some of the deeper strangeness that all of this points toward. Because the speed of light is not just a number. It's a horizon, a limit. And limits, in physics, are often the most interesting things. When you move at high speed relative to a stationary observer, your time slows and your length contracts. As you approach the speed of light, time slows to nearly zero and your length contracts to nearly zero. At the speed of light, time doesn't pass at all. The photon, if we could ask it, would report that it traveled from the star to your eye in no time at all. The journey took 0 seconds. The distance was zero. From the photon's perspective, if a photon can be said to have a perspective, the star and your eye are in the same place, at the same moment. The universe, for light, has no extent and no duration. It all collapses to a point, to an instant. What we experience as the vast, ancient cosmos, billions of light years in diameter, billions of years old, is, for the photon, a zero-distance, zero-duration trip. This is very strange to think about, and I don't mean it as a casual observation. Physicists genuinely don't quite know what to do with the photon's perspective because photons don't have reference frames in the usual sense. Special relativity's equations produce infinities when you try to apply them to an observer traveling at exactly c. The photon is, in some sense, outside the framework that describes the rest of physics. It exists in a different relationship to space-time than anything with mass. And yet it's the constant that defines space-time. It's the speed limit that makes causality work, that ensures causes always precede effects, that information doesn't travel backward in time, that the universe has a coherent structure of before and after. Without c, the arrow of time would have no foundation. The speed of light is the number that holds reality together. Now let me tell you about something that might be the most quietly astonishing consequence of everything we've discussed. The light that made the image of the Andromeda Galaxy on the photographic plates of early astronomers left Andromeda about 2.5 million years ago. When it left, Homo erectus was just beginning to appear in Africa. There were no human beings yet, no fire, no tools beyond the crudest stone. And the light that left Andromeda at that moment traveled through empty space for 2.5 million years, threading between galaxies, unchanged and undimmed except by the gentle expansion of the universe. And it arrived at our photographic plates at the exact moment an astronomer was pointing a telescope in that direction. The light doesn't know it waited for us. It doesn't know that we were here to receive it. It simply traveled, at c, the same speed it always travels, arriving when the geometry of the situation said it would arrive. When astronomers look at distant objects, they are looking at the past. They are seeing light that is genuinely ancient, that encoded information about its source millions or billions of years before that information could be received by anyone. In some sense, the sky is a history book, but one written in light, and the deeper you look, the further back in time you see. The most distant objects we can observe emitted their light about 13 billion years ago, when the universe was only a few 100 million years old. We are seeing those objects not as they are now, but as they were then. Whether they still exist, whether the galaxies and quasars at the edge of our observable universe are still there in any recognizable form, we don't know, because the light that would carry that information hasn't reached us yet. It won't reach us for billions of years. There is a sphere around us, called the observable universe, beyond which we simply cannot see, not because there's nothing there, but because the light from further out hasn't had time to reach us in the 13.8 billion years since the Big Bang. We are surrounded by a horizon, set by the speed of light and the age of the universe, beyond which the cosmos is invisible to us. Not hidden, just unreachable. Not yet. If intelligent beings exist on a planet 14 billion light-years away from us, which might itself be impossible, since the observable universe is only about 46 billion light-years in radius due to the expansion of space, we could never communicate with them. Not because we lack the technology, but because even a signal traveling at the speed of light would take longer to reach them than the current age of the universe. And thanks to the accelerating expansion of the universe, the gap is actually growing. Some distant regions of the cosmos are, in a physically meaningful sense, permanently beyond our reach. The universe is not obligated to be reachable. It is not obligated to be observable. It is not obligated to be knowable. And the speed of light is one of the key parameters that determines how much of it we can ever hope to know. This feels like a vast and somewhat melancholy thought, and perhaps it is. But there's something else in it, something more comforting, if you turn it the right way. Everything you've ever seen, every star you've observed, every photograph of a distant galaxy, every image from the Hubble or James Webb Space Telescope, is made of light that traveled across distances and timescales almost unimaginable to human intuition and arrived here, at this planet, at this moment, at these eyes. The universe has been sending us messages, continuously, since before there was anyone to receive them. And now there is. Now we're here, and we're reading them. The ancient light from dying stars falls on you every clear night. You look up and see history, cosmic history, billions of years of it, because light travels at a finite speed and time passes and the universe is very, very old. If light were truly instantaneous, you would only ever see the universe as it is right now, in this instant, everywhere at once. There would be no echo, no past preserved in light, no window into the history of the cosmos. The finite speed of light is what makes the sky an archive. There is one more thread I want to follow before we let this go, and it concerns something that might seem, at first, like a detour, but which is actually where the story of light and speed and the strangeness of the universe arrives at something deeply personal to every living thing on Earth. The sun is about 8 light minutes away. The light warming your skin on a summer afternoon left the sun about 8 minutes before it reached you. The energy in that light was generated in the sun's core by nuclear fusion, hydrogen nuclei colliding and fusing under enormous pressure, releasing energy according to Einstein's equation EMC superscript 2. But the photons produced in the core don't travel to the surface instantly. They take a long time. Estimates range from a few thousand to hundreds of thousands of years, because the interior of the sun is extraordinarily dense, and light scatters and is absorbed and re-emitted so many times before escaping. A photon might travel only a centimeter before being absorbed by another particle and re-emitted in a random direction. The process of random walking from the core to the surface is slow. When a photon finally reaches the solar surface and escapes into space, it then travels across 150 million kilometers of vacuum in about 8 minutes and arrives at Earth, where it may be absorbed by a leaf and converted by photosynthesis into chemical energy and incorporated into a plant and eaten by an animal and metabolized. The energy that is keeping you alive right now, the warmth in your body, the electrical signals in your neurons, the small motion of your lungs as you breathe, is energy that was locked inside hydrogen atoms in the sun, released by fusion, carried across 150 million kilometers by photons traveling at 299,792 kilometers per second, captured by photosynthesis somewhere in the food chain, and eventually incorporated into you. You are, in the most literal physical sense, made of starlight. Not as a metaphor, as a fact. Every atom in your body was forged in the interior of a star. The carbon in your bones, the oxygen in your lungs, the iron in your blood, elements heavier than helium can only be produced by stellar nucleosynthesis, by the same fusion processes that power the sun. When massive stars run out of fuel and explode as supernovae, they scatter those elements across space, where they eventually coalesce into new solar systems, new planets, new oceans, new life. The universe made you out of old stars. And the energy keeping you alive right now is fresh starlight, 8 minutes old, from the nearest one. If you want to feel what the speed of light means at a personal level, this is it. It means that the connection between you and the sun is not abstract. It's not symbolic. It's a continuous stream of photons, traveling at sea, arriving every second, sustaining everything. I want to come back, gently, to where we started, to the room you're in, to the light, if any remains, settling around you. We've traveled a long way tonight. From Galileo's hillside lantern experiment in the 1600s to Ole Romer painstakingly tabulating the eclipses of Io from a Paris observatory, calculating, for the first time, that light takes time to travel. We followed Albert Michelson in his obsessive, decades-long pursuit of a more precise value, building longer and longer instruments, chasing another decimal place with a patience that bordered on the devotional. We watched James Clerk Maxwell sit down with the equations of electricity and magnetism and find, buried inside them, the speed of a wave he recognized, with some amazement, as light itself. And we watched a young patent clerk in Bern take Maxwell's constant and ask, what if this isn't a speed relative to some medium? What if it's a fundamental feature of the universe? What if we take it seriously? And then we followed what happens when you take it seriously. Time dilates. Space contracts. Simultaneity breaks. Mass and energy become equivalent. Gravity curves space-time and bends the path of light. Black holes exist. Gravitational waves travel at sea across the universe. GPS satellites need relativistic corrections. The internet runs on laser light and glass fibers. And you, lying here, are alive because photons left the sun 8 minutes ago and haven't stopped coming. The speed of light is one number, 299,792.458 kilometers per second. And woven into that number is the architecture of reality. Time, space, energy, mass, causality, the structure of the observable universe. It is not a coincidence that it keeps showing up everywhere in the deepest equations of physics. It is, in some sense, the number that holds the whole thing together. In 1676, Ole Romer stood before the French Academy of Sciences and said, in effect, light takes time to arrive. The universe is not instantaneous. Effects do not propagate immediately. There is a delay, and that delay has a definite rate. Almost no one fully believed him at the time. The idea was too strange, too counterintuitive, too much a violation of the sense, obvious to any ordinary person, that light just is, that it arrives as soon as its source exists, that it doesn't travel in any meaningful sense. And now here we are, 3.5 centuries later, measuring gravitational waves from black hole mergers a billion light-years away, using laser interferometers sensitive to atomic-scale vibrations, correcting GPS satellites for relativistic time dilation, transmitting the sum of human knowledge down glass fibers at 2/3 the speed of light, and understanding, in exhaustive mathematical detail, why that number, c, is exactly what it is and why it cannot be otherwise. The universe doesn't slow down for us. It doesn't make its rules intuitive. It doesn't arrange itself so that the truth is obvious to casual inspection. The speed of light seems instantaneous from where we stand, until you look carefully enough, until you watch the moons of Jupiter, until you build a detector sensitive enough, until you follow the mathematics wherever it leads. And then the universe opens up, and it is stranger and more wonderful than the intuitive version. And the strangeness is not a barrier, it's the reward. You've traveled a long way tonight. The ideas can settle now, the way things do when you stop trying to hold them and just let them be. The room around you is real and ordinary and warm and full of light. Even now, even in the dark, photons of infrared heat radiating from every surface, from your own skin, from the walls, crossing the room at sea in the tiny fractions of a second it takes them to travel a few feet. The speed of light is everywhere. Even here. Even now. It always has been. Let that be the last thought. There's one more thing I want to give you before we let the night fully take over. It's not a fact exactly, more of a way of holding all of this. When you look at the night sky, on a clear night, away from city lights, where the stars are properly visible, you're looking at a picture that isn't quite real. What you're seeing isn't the sky as it is right now. You're seeing a composite image assembled from light that left its sources at many different times. The moon you see left the moon about 1.3 seconds ago. The light from Venus left Venus somewhere between 2 and 14 minutes ago, depending on where in its orbit it is. The star Sirius, the brightest star in the night sky, sent you the light you're seeing about 8.6 years ago. The Orion Nebula's glow left there about 1,300 years ago, when the Tang dynasty was flourishing in China and the Islamic Golden Age was just beginning in the Arab world. And those are the nearby ones. When you look at the Andromeda Galaxy, just barely visible to the naked eye as a faint smear of light near the constellation Andromeda, you're seeing light that left there 2.5 million years ago, before there were human beings, before our ancestors had language. That light has been traveling through empty space since before anyone was here to receive it, and tonight it arrives at your eyes, and you see a faint smudge of ancient light against a dark sky, and you can know, because of everything we've talked about tonight, what that smudge is and how far it's traveled and how old its news is. The sky is not a window. It's a time machine. And the reason is c, the finite, definite, invariant, wonderful speed of light. 3.5 centuries of increasingly careful measurement, from Galileo's covered lanterns to Michelson's mercury-floated sandstone slab to femtosecond laser pulses in cryogenic optical cavities. All of it converging on a single number that was always there, always the same, waiting patiently for us to understand what it was. 299,792.458 kilometers per second. Exactly. It doesn't change. It never changes. It was the same when the photons now arriving from Andromeda left their source 2.5 million years ago. It will be the same when our own sun expands and Earth is swallowed billions of years from now. It's one of the few things in the universe that deserves the word constant in a fully literal sense. And that constancy, that absolute, invariant reliability, is not a cold or indifferent thing. It's what makes time meaningful. It's what makes distance meaningful. It's what makes the past visible in the sky and the future predictable from equations. It's what connects a photon emitted in a distant star to an eye in a dark room on a small planet. It connects you, right now, in this room, to the history of the cosmos. The light arriving at your closed eyelids from whatever glow remains in the room, traveling at sea. The infrared warmth radiating from your own body into the air around you, traveling at sea. The microwaves bouncing off the walls from your phone's wireless signals, traveling at sea. All of it, everywhere, all the time. The speed of light is not a limit on the universe. It is the universe, in some important sense. It is the rate at which cause propagates to effect, the rate at which the past informs the present, the rate at which a collapsing star across the galaxy can, billions of years later, warm the face of a creature that evolved to be curious about it. That's enough, I think. Let the numbers go. Let the history go. Let even the wonder go for now. The universe will keep its speed while you sleep. And it will be there, exactly the same, exactly as strange, exactly as beautiful, when you're ready to look again. Good night.